we're going to be looking at powers and exponents. And what we're looking at essentially is how do we look at really big numbers or really small numbers, okay? And today we're going to be looking at really big numbers. So I want you to consider the following poem. As I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Each cat had 7 kits. Kits, cats, sacks, wives. How many were going to St. Ives? So this is an old nursery rhyme. And what I want you to think about is, what is a strategy that you could use to determine how many total there are going to St. Ives? Now, when we say total, we're excluding yourself and the husband, okay? The question says kits, cats, sacks, and wives. And there are a couple different options. So we could count and we could think, okay, there's the husband. There's his 7 wives. And each 7 wives had 7 sacks. And each 7 sacks had 7 cats. That's a lot of counting. And we haven't even gotten to the cat's kittens yet, of which each cat has 7 kittens. Right? I give up 2. And yet we still have all those kittens. So we could count and go through, count all the wives, count all the sacks, count all the cats, count all their kittens, but that's going to take us a really long time. So good news is there's another option. One of the things that we can do is we can look at what's called exponents and using powers in order to solve this problem. So the number of wives is 7. The number of sacks is 7 times 7 because each wife had 7 sacks. So we have to multiply those together. Now, each of those sacks has 7 cats. So we have to multiply the number of wives times the number of sacks times the number of cats in each one of those sacks to determine the number of cats. Finally, each of those cats has 7 kittens. So we have to multiply the number of cats times the number times 7 for each kitten that the cats have. So when we look at that total, the number of wives is 7. We have 49 total sacks. Each sack has 7 cats. So we have 243 total cats. And each one of those cats has 7 kittens, which means that we have 1,701 kittens. It's a lot of kittens. Now, if we look at the total, the question, if you remember, is asking us how many wives, sacks, cats, and kits there are. So if we add all of those up, we get 2,000 total kits, cats, sacks, and wives. All right. Now, the way we did this was by using exponents. So what we looked at was we looked at the power, which is a product of repeated factors. Okay. In this case, our power for example, maybe kittens was to the 4th power, 7 to the 4th power because there were 4 of them. Our base in this case was 7. 7 was our base number that we were dealing with every time that we had to multiply itself. And a base of a power is the repeated factor. The exponent of a power indicates the number of times the base is being used as a factor, okay? So the whole thing is called the power. The base is our number that is being the repeated factor that's being multiplied. And then our exponent is that little number up top in the air that tells us how many times the base is being multiplied by itself. Remember, exponents, this is not 3 times 4. This is 3 times 3 times 3 times 3. 3 is being multiplied by itself 4 times. Now, a couple terminology things that we could say is whenever we have 3 raised to the 2nd power, we can call that 3 squared. And I'll tell you why in a second. Or we say 3 to the 2nd power. When we have 3 as our base, or any number is our base, and it's raised to an exponent of 3, we say that's 3 cubed. Or 3 to the 3rd power. Anything beyond 3 to the 3rd power, we just say is 3 to the whatever power. 3 to the 4th, 3 to the 5th, 3 to the 6th power, 3 to the millionth power, whatever that is, okay? The only two that have different ones are 3 squared and 3 cubed. Okay, so one of the things that we're going to be looking at is writing expressions as powers. When we have 12 times 12 times 12 times 12, 12 is the number that's being multiplied by itself. So 12 is going to be our base, and it's being multiplied 4 times, so we get 12 to the 4th power. Our next example is we have a base of 4, and there are 5 4s here, so we have 4 being raised to the 5th power. We can also do this with variables. So here we have x times x times x times x times x times x. We have 6 of them, so that makes that our 6th exponent, and our base is going to be x to the 6th power. Now, sometimes you might see different bases, and our different bases, when they're being multiplied by each other, still need to stay separate. So we have 2 times 2 times 2, which is 2 to the 3rd power, and then we have b times b, 2 b's, so b squared. So this ends up becoming 2 to the 3rd power times b squared. Now, when you work backwards and you are given the power, what you're going to have to see is that we have to kind of go backwards now. So if we're given 7 squared, or 7 to the 2nd power, this is really going to be 7 times 7. And this 5 to the 3rd power is really going to be 5 times 5 times 5. Remember, it's repeated multiplication of the same factor. This is not 7 times 2, and this is not 5 times 3. So when we pull out 7 squared, we get 7 times 7, we get 49. When we pull out 5 cubed, 5 times 5 times 5, we get 125. Okay, perfect squares. So if you look at this square here, you can see that our width here, we have 3 squares. Our height is going to be over here on the left-hand side, where we have also 3 squares. This is why it's called a perfect square. This is also why it's called 3 squared, because there's 2 of them, okay? Width times height, or length times width, same thing. So a perfect square would be, in this case, 9 square units, because there are 3 on the bottom and 3 going up. 3 times 3 is 9, and we get 9 units here. Mind blown, right? Okay, so one of the things you're also going to be looking at in this section is a square, what's called a perfect square, okay? And we have lists of perfect squares. 9 is our example here. 9 is a perfect square, and it is a perfect square because it's the square of 3. 3's here, 3's here, and we get 9. A list of perfect squares is here for you to see. And one thing that I do want you to be able to see here is that all these numbers over here on the right-hand side are all going to be your perfect squares. And they're perfect because they are the actual square of our whole numbers here. Anytime you take a whole number and you square it, whatever the product is, that's your perfect square. So these over here are all examples of perfect squares. They're a good list for you to memorize, just like your multiplication tables.